Good morning. The previous lecture was, in a sense, optimistic. It was the class of problem where the distance concept did work. We could globally extend some transcendental geometric object. The lecture, it will be about no extension, no global extension of something. So what it is about? Lecture 4 is no extension of holonomy. For sure, there is a possibility of some extension, but no universal, no global extension of the holonomy. So, what is the holonomy? I will try to find a better chalk. Thank you. Mm-hmm. In the real case, I recall you that this is the Poincaré map. And this is the holonomy map. The Poincaré map, is a map by the orbits from a cross-section to itself. And the holonomy map is very similar. It is a map along the orbits of one cross-section to another. So we will deal with the polynomial equations in the complex plane. We are now in the C square. And we will take one complex line, gamma 1, transversal to the orbits. It may be tangent at some isolated points, no matter. Another one. And a map of one cross-section to another. This is, in fact, the complex phase curve, a Riemann surface. But it intersects the cross-sections at isolated points. So you have a real curve on the Riemann surface from one cross-section to another, and the complex existence and analytic dependence theorem for solutions asserts, guarantees that from the nearby points, you can pass to the nearby points of the target along a curve on a Riemann surface on the leaf of the foliation. So this is the complex holonomy map H. And the question is the following. You have definitely a local holonomy map. Its existence is guaranteed by the existence and uniqueness and analytic dependence theorem for complex differential equations. The question is about the global extension. Given an arbitrary curve gamma in gamma 1, is it possible to analytically continue to extend the holonomy map along gamma? If not, we will be satisfied by the extension along gamma epsilon, which is epsilon close to gamma. And the answer is no in general. And this is a groundbreaking result by Calsamiglia, Deron, Frankel, and Adolfo Guyot, who is present here. So this is the general goal of my lecture today, to explain this phenomenon. And here is a very non-homogeneous audience, students up to bachelor ones and mature colleagues, mature investigators. The beginning part of this lecture will be oriented to students. I want to show you some elementary things, sometimes even included as parts of the general course of differential equations, just so that you will be accustomed to the major notions that I will use in the second part of the lecture. So, an example. What is the most simple differential equation in the world? I should say, if your variable is r dot equals 0. What is next simple equation? I should say r dot equals r. And if r dot is dr over dt and t varies in the circle, then surprisingly there is something non-trivial related to this simplest equation. When t is on the circle, then the phase space is the cylinder. We have a point r equals 0 and the periodic solution, because t runs over the circle, r equals 0. Then we have a monodromy map delta. The Poincaré map, the monodromy map, they are synonymous, and delta of r equals r multiplied by e power 2 pi. So up to now, nothing interesting, nothing surprising. There is a global map. It is called a monodromy map. Of the section which call it gamma 1, t equals 0. And I take another section, gamma 2, r equal constant, I do not write that. And I consider the holonomy map from gamma 1 to gamma 2. It is well defined in the neighborhood of the intersection point. And when we continue it, then it comes to the whole of gamma 2 when you use the segment so-called fundamental domain of the holonomy map. That is, the images of this segment under the holonomy map cover all the line under positive iterates and under negative iterates. Not all the line. It is important that they cover the whole ray like this. So if you try to extend the holonomy map along this ray, then you are successful until you come to 0 exclusively. The image of the monodromy map, inverse monodromy map, e to the negative 2 pi, of this segment is this segment, smaller segment. And when we extend the holonomy map to this segment, we see the following. The phase curve starts from this point, makes a wind, and comes to this segment, because the inverse monodromy map brings this segment to this segment. So the curve starts from these small segments, comes to this large segment, and then comes to here. So when you run along these two segments, the image makes one wind around this yellow curve, and then some arc. When you take the nth pre-image of this segment under the inverse monodromy map, then the image of the point on the larger segment runs n times along the yellow curve, and then runs a small arc. And it cannot be extended to this point, to this cycle. And this is a key example for the most important part at the end of the lecture. So it is absolutely elementary. I should repeat that, in my opinion, it is a second simplest equation in the theory of differential equations at all. So now, in order to get you accustomed to the notion of the monodromy map, I will show you a part of the general course of differential equations, linear periodic equations. That is, I will change z to x dot equals to a of t x plus b of t, and ab of t plus the period t are explicitly ab of t. So I am lazy, I should write b of this equals to b of this, and a of this equals to a of this, and this means the union. Okay? No problem with that. Well, we could factorize the real line over t and consider a cylinder. S1 equals to r over tz. Then we get again a cylinder and a monodromy map of this line, say t equals 0, to itself. So phi of t x is a solution such that phi of 0x equals x. So if this is x, then this is the graph of phi. And there is a monodromy map, M, x to phi of tx. A question to students. What is known about this monodromy map? So here is a proposition, a claim. What is phi? Almost. Linear means that it is x to lambda x. And it is similar to linear, a second attempt. Great. And A is an exponent of the integral over the period of the function a of t. As you can integrate this equation, this is just an exercise, and unfortunately, if I should give a student lecture, I will explain this. But I have a lot of things to tell you, even in 1 hour, so I stop here and say that it is a good exercise. Now, consider a complex Fuchsian equation. This is, again, one-dimensional equation on the complex line. Dimensional, so solvable, not interesting. Fuchsian means that A of t has only simple poles on the whole Riemann sphere. So A of t equals to the sum of lambda j t minus aj. The poles are at the points aj, and lambda j are so-called residues. So the solution is a product of t minus aj power lambda j multiplied to the initial condition. We suppose that none of aj's equals 0. This is an exercise and an exercise in differential equations and elementary functions of one complex variable. So we have a picture, and a similar picture will be plotted several times later. These are AJs, A1, AK. This is 0. And when you take a simple loop around alpha j, say this is AJ. When you take a simple loop around AJ, then you can consider a monodromy map you start here from z of 0, and you make a circuit, and you come along the phase curve. This is a curve on the Riemann surface, a curve on the leaf that covers this loop under the projection along the z-axis. This is the t-axis. This is the z-axis. And you have the map mj. And as in the real case, mj, you take a point zeta here, equals to exponential of 2 pi lambda j zeta. I understand quite well that I am too fast and it is difficult for you to prove in mind what I am saying. But if you have more time to look at all of this, you will easily prove everything that I am saying here in this section. So, the complex case differs from the real one by the fact that the t-axis has much more rich topology than the real t-axis, which may be a real line or a real circle. For instance, the t-axis with the pole of the coefficients deleted is a Riemann sphere with several points, with several punctures, and it has a rich fundamental group. If you have n punctures, then the fundamental group will be free of rank n minus 1. So the monodromy group is the group you pass one curve, then another curve, and you extend the solution along this product of two loops, and the monodromy maps are multiplied. So if you take any element from the fundamental group of the punctured sphere, you have a corresponding element of the monodromy group, and it is a product of these multipliers corresponding to the loop in the fundamental. So you have the whole monodromy group the monodromy group M is a group generated by MJs. On one hand, we are in a very elementary realm, the realm of complex elementary functions of one variable. All the formulas are explicit, all the solutions may be calculated, so nothing mysterious. On the other hand, a group with the operation, what is the operation in this group? When we pass two loops, two loops, what will be the result, what will be the monodromy mapping, how it is expressed through the monodromy maps for every of these two loops. You make one circuit, one monodromy map, then another circuit, another monodromy map. What is the resulting monodromy? Every monodromy map is a multiplication by a corresponding complex number. What is the result of two successive monodromy? You make one circuit, then another circuit. At this circuit, you multiply by mu1, say. At this circuit, you multiply by mu2. What is the resulting monodromy map? It is the product, and the group operation is multiplication. So, even a group with the multiplication is very interesting and, in a sense, non-trivial. First of all, this group for a generic pair, lambda and mu, is dense in C. So if you take all possible products of lambda and mu in positive and negative integer powers, then you get a countable set of complex numbers which is dense on C. And this is, again, a problem solvable by students. On the other hand, it is not structurally stable. This means that if you slightly change the two numbers lambda and mu, you cannot find a homeomorphism that will bring the corresponding elements of one group, lambda and mu in the same powers, to the corresponding elements of another group, lambda and mu perturbed at the same powers. You cannot find a homeomorphism of the complex line that will bring the orbit of one group to a corresponding orbit of another. This is once again a student problem. So I ended up my elementary and I switch to a more advanced part. Still not far from elementary. The Riemann-Hilbert problem. Consider once again a Fuchsian system now in dimension n. Very similar to what I have written, only lambda j's are replaced by matrices. Z is now in Cn, and is in the space of matrices of order n. They are called matrix residues. So the same picture holds, but now this is not C1 as was previously. Z now runs not over C1, but over Cn. All the rest remains the same. And you have zero is different from AJs. You have once again the monodromy group, which is a curve gamma j surrounding AJ is covered by a curve on the solution, and you get a monodromy map. Once again, it is easy to prove for a monodromy map MJ corresponds to the curve gamma j, and MJ is linear. In the one-dimensional case, it was a multiplication by a well-known number. In the multidimensional case, it is a good puzzle to calculate the monodromy map given the residue maps and the poles AJ. There was a lot of work related to that. I should mention a name of Russian mathematician Lappa Danilevsky of the first half of the 20th century. And we should praise the name of Riemann, who discovered all these concepts, all these effects of analytic continuation and monodromy maps. One natural problem is, given the residue matrices, find the monodromy operators. So a question for those who did not hear this before. What is a next natural problem? A next natural problem is inverse. Given the monodromy operators, find the residue ones. And Riemann stated this problem. This is the Riemann-Hilbert problem. Given the monodromy operators, find the residue ones. I am not certain whether Riemann was sure that this problem is always solvable, but he could not solve it. And this problem persisted during all the 19th century, and David Hilbert, in his famous talk of 1900, included this question in his famous list of 23 problems. It was Hilbert's 21st problem. And as far as I remember, he stated the problem in the following form. Prove that for any tuple of the monodromy maps, there exists a tuple of residue matrices. What I said is definitely different from what Hilbert said. He said something more vague, and this is only one of the possible interpretations of what he said. But he was definitely certain that the solution is positive. And there was a dramatic history of this problem. At the beginning of the 20th century, Josip Plemel solved this problem and proved that for any monodromy maps, you can find a corresponding tuple of residue matrices. And at the beginning of 70s, I studied thoroughly his proof. Amazingly, he published his proof in details only in 1962. And I found that his arguments gave the positive solution only in assumption that one of the MJs was diagonalizable. So its Jordan normal form had no non-trivial Jordan cells. In this case, really the answer is positive. But when Jordan cells are present, the question was open. And only in 1989, Andrei Bolibruch quite unexpectedly found a negative solution of this question. Not every tuple of MJs might be realized by the Fuchsian equation. So this is the story slightly aside my main topic, but I wanted to tell it to you because it is one of the most dramatic and most important subjects in the theory of complex differentials. So let us go back to this situation. The negative solution exists for n greater or equal to 3. And in dimension 1, you can prove yourself that given monodromy maps, you can find residue matrices which are simply complex number. The answer is positive for n equal 1 and 2, negative for n greater or equal to 3, and this is Willebroek, 1989. So let us consider the case of n equal to 2. Let us for a while forget about the Riemann-Hilbert problem and concentrate on the two-dimensional linear system. Now here n equals 2. Then you can pass to a one-dimensional equation, which is called the Riccati equation. In the Fuchsian equation that I wrote, Z belongs to C2. You take W equal to Z1 over Z2, and you can find a nonlinear one-dimensional equation with respect to now A of t is probably the sum like that or something other. In any case, A of t is a matrix A, B, C, D depending on t. And it appears that W will satisfy a nonlinear equation. It will be B plus A minus D Z if I do properly remember, an equation like this. This is a Riccati equation. And the monodromy for this system was linear. The monodromy for the Riccati equation, as this is two components that of a vector that undergoes a linear map, the Riccati equation will have a fractional linear monodromy. Is a Möbius transformation. like alpha W plus beta divided of gamma W plus delta. And as the Riemann-Hilbert problem for two-dimensional linear systems has a positive solution, the Riccati equation produced by this linear system, that is A, B, C, D, have simple poles, will also admit a monodromy group, and any monodromy group of Möbius transformations may be realized by the Riccati equation. Thank you very much. Certainly, this is W. So I come to the major point of my lecture, holonomy of the Riccati equation. We have the Riccati equation. This is the t-axis. These are the straight lines parallel to the z. Let me change W to z. I am more acquainted to this, accustomed to this. This is the z-axis. These are AJ, AK, a 0, which is not equal to any of the AJs. And you have monodromy maps. And you are interested in the holonomy map. Say this is gamma 1. And a plane z equal to z0 is gamma 2. They intersect in some point, and near this point, a holonomy map H from gamma 1 to gamma 2 is well defined. So I want to extend this map H along an arbitrary curve gamma inside gamma 1. Or at least find a nearby, an epsilon closed curve along which I will be able to extend this map. And in the work of the four authors that I quoted before, is proved that this is impossible. And there is even more to say. Definition. Say G is the monodromy group. It acts by the Möbius transformations but for this definition, it is not important. A point zeta is a limit point of G if exists zeta 0 and the sequence Gn is G such that the images of the point zeta 0 under Gn accumulate to Z. So when you take zeta 0 and all the images of this point under all the transformations from G, from the group G, you get an orbit. And a limit point of the group is a limit point of an orbit. So the point is a limit point of the group if there exists an orbit for which it is a limit point. And this is the definition of a limit point of the orbit and therefore of the group. Okay? So the theorem, which is definitely present in the work that I quoted, but probably present between the lines, is the following. The holonomy map described above cannot be extended. Let me make a break here. I prefer to write some assumptions of the theorem above the statement. So let the group G contain a subgroup G plus such that exists a domain omega in C in which G plus is contracting. That is for any G in G plus, the domain omega comes to itself, and G in omega is contracting, that is decreases the distance between each 2 points, at least by this distance multiplied by some number smaller than 1, and the same for all the pairs of points in omega. So the holonomy map H cannot be extended. G plus is but a semi-subgroup. That is, only positive powers of the maps are allowed. You cannot take an inverse map. An inverse to contracting is expanding. But you take a semi-group that is products of this set of the maps from this set in the positive powers. Then all the products are also contracting if the factors are contracting. So the holonomy map H cannot be extended to the limit set of G plus. I make an exclusion from my rules, and I give the proof of this theorem for you, though the time left is short. The proof is, it will be a sketch of the proof, not the complete proof. Take any element G from this subgroup G plus. It is contracting in omega, therefore it has a fixed point, zeta G. A fixed point of a monodromy map corresponds to a closed curve on the solution. This is gamma G. This is our curve, gamma 2. This is the t-axis. And omega is located in gamma 1. Let us project this curve both to the t-axis and lift it along the lines t equal to constant to the gamma 2 axis. Then we will get a picture analogous to the one that we had in the beginning of the lecture. Only these lines are now complex rather than real. I said that I give a sketch of the proof. So by the same reason as before, we cannot extend the holonomy map along the following curve. This omega is in the complex plane gamma 1, and let us plot a curve inside. This was the projection along this complex curve. Let us plot the following curve. Let us take the holonomy map H and the inverse image of this curve. This will be some arc. Then let us iterate. This arc has two endpoints, and the upper one is the image under the monodromy map along this curve of the lower one. And let us iterate the map G. Then this arc will converge to the only fixed point of the map G in the domain omega. And the holonomy map H cannot be extended up to the end of this curve. This curve is a union of a finite number of exponentially decreasing arcs, and its endpoint is the closure. And you cannot extend up to this endpoint the holonomy map. And it is not difficult to construct a limit set that contains a triangle. This will be a triangle inside the domain omega with the vertices zeta corresponding to G1, zeta corresponding to G2, that is fixed point of G1, fixed point of G2, fixed point of G3. I need to have 3 elements. And this triangle will all belong to the set of limit points of G plus, to which we cannot extend the holonomy map. So this is the non-extendability result that I wanted to sketch for you. I hope that it is possible to restore all the details if you are eager enough, but it can be found in the textbook of Singularities in Dynamical Systems, edited by Springer, with Jose Seade, one of the editors. In the volume 5, there is a chapter written by me, and all this is included in this chapter. Thank you. Are there any questions? In fact, we can construct, using the solution of the Riemann-Hilbert problem, a non-homogeneous equation for which the GJs will be affine. So you have a rather elementary problem. You have 3 affine maps. Both are contracting. AJ is real, smaller, real positive and smaller than 1. And this becomes an elementary problem to prove that the limit set of the group generated by 3 affine maps contains a triangle with the vertices fixed points of these maps. So This is an elementary statement. I should not say that it is very simple. AJs should be not only smaller than 1, but they are close to 1 in such a way that the image of this rectangle under the 3 maps covers this rectangle. So apply G1. It fixes this point, and it is just linear with respect to this point. So it brings this triangle to this one. And when you apply G2, you bring this triangle to this one. And when you apply G3, you bring this triangle. Let me find some other color. To this one. So this is the first step of constructing the fractal picture. In fact, if you want that your original triangle remembers this covering, then each one of the colored triangles is covered by smaller 3 triangles. And if you want that these smaller triangles remember the original covering, then you have now, there were 9 smaller triangles that cover this one. After that, there will be 3 to cube smaller triangles that cover this one. And this goes to infinity. And for any sequence of smaller triangles, you can find a limit. For any point in this large triangle, you can find a sequence of smaller and smaller triangles that converge to this point. So this is why the whole triangle belongs to the limit set generated by a contracting group.
Any other question? ¿Más preguntas? No. Well, in this complex function equations, so I'm here. Yes. So this T belongs to the sphere minus some points, no? But I don't know if you said what happens if you take something with a more topology like torus or another Riemann surface without some points. What change in this situation? In this function equation, this linear.
Do you want to change this linear equation?
No, the second blackboard in the middle. Yes, this.
Blackboard.
Yes?
Yes?
If T belongs to another Riemann surface with genus plus or equal to 1?
There is a similar theory, but it is parallel and not complicated. There are similar results if the Riemann sphere is replaced by another Riemann surface.
Any other question?
It should be compact.
Compact, okay. Okay. But you have to take these singularities, no?
If you have a non-compact Riemann surface, then the Riemann-Hilbert problem is always positively solved.
¿Más preguntas? No. If no, let's thank Yulij again.